Whoa! 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 Have you ever been on a roller coaster? Well, that's where we're starting. Welcome to lesson 1.2 Characteristics of Functions and Graphs. And to spark our learning, we are here at a roller coaster place. Uh oh, my face went away. There I am. So here we have Brianna's roller coaster has a steeper. Oh wait, no, go back. Brianna and Denver rode different roller coasters. They both claimed their coaster was more exciting. And naturally, what is a mathematical question you can ask about this situation? What information would you need to know about your answer? So, if you look at the picture, obviously one of them has a steeper drop. According to this one, Denver's roller coaster climbs higher. It's debatable, but whatever. Might be true. You know, we could ask like how fast they're going, how long they're going, things like that. But what I really want to bring your attention to is this idea of a roller coaster going up and going down. So if it's going up right here, we could say it's increasing, hint, hint, wink, wink. If it's going down, we can call it maybe decreasing. So think about this roller coaster thing because it's going to come back over and over again. So let's get started. This section is about characteristics of functions and graphs. Basically, it's an introduction, and there's going to be a little bit of vocabulary in this section. So hang on tight. But anyway, so this says sketch a function graph from a verbal description. So here is a real world situation, kind of, sort of, and it wants us to write a graph about it. So you can sketch a graph of a function from a description of its key features. Consider this situation. A dam controls a reservoir's water level. The level is currently steady and above normal. To prepare for coming rain, engineers will lower the water level at a constant rate until it is below normal. The water level is expected to rise rapidly with the rains and gradually level off well above the current level. You can sketch the graph of the reservoir's water level as a function of time, where the normal water level of the reservoir is represented by the horizontal axis. So they have obviously already done this for us. So they had mentioned that the water level, so this is our quote-unquote normal water level right there. Let's see if I can use my fancy pen. So here is our normal water level. And then it said it started above normal. And, you know, there's a numerical value here. And I'm sure that's what that point is. And it remained constant. But then engineers dropped the water level at a constant rate. So that's why there's a line. So this would be decreasing the water level until they got to a certain whatever. So I guess 10 feet below the normal water level. And then it rained and it rapidly increased. And then it looks like it continued to increase, but it leveled off a little bit. And it ended higher than where it started. So a couple of things that we should note. So there's, I guess, 4 sets of words that we're going to talk about real quick. There's increasing and decreasing, and then positive and negative. So don't get those 4 words confused. So this graph is positive anytime it is above the x-axis. So if I were to ask you, what interval is this graph positive, you would say 0 to, what is that, 4, 7. We'll pretend that that's 7. So that is where it is positive. That is this chunk right here. And then that is, again, this chunk right here. So then we could say It's 8, 9, 10. We'll say that's 11. I'm making some of these numbers up. 11 to 18. So those are the intervals where the graph is positive. So then the exact opposite, the graph is negative anywhere where it is below the x-axis. So that is positive and negative. That refers to these y values over here. So positive, negative. The other two words that I wanted to mention is increasing and decreasing. That's where the roller coaster analogy comes into play. So as you're moving left to right, if you were going down, you are decreasing. If you were going up, you are increasing. So again, for example, our graph is decreasing from here to there. What did I say? It's decreasing. So our graph is decreasing along this whole interval. Our graph is then increasing from here all the way up to there. By the way, I'm not going to be a stickler about this, but the book might be. If you were to say, or if the question was, what interval is this graph decreasing at? So that would be from here to there. You would not include these dots. So they would be parentheses. So that would be like, what, 5 to 9-ish. Notice that there are parentheses as opposed to square brackets, because at this point the graph is neither increasing nor decreasing, it's just there. So again, not something I'm going to gig you on a test, but sometimes the book gets a little crazy. So quick review: positive, positive, negative, decreasing, increasing. What are some of the other words that I missed? So the minimum is just the lowest point in the graph, and the maximum is the highest point of the graph. Those I think are kind of easier to remember. And let's see here, I forgot turning point. Turning point is whenever a graph goes from decreasing to increasing or increasing from decreasing. So turning point is going to be a lot more important when it comes to like parabolas, things like that. So increasing, we talked about. Decreasing, there's the scientific definition, the mathematical precise definition, but it's what I kind of told you. Turning point, where the function changes from increase to decreasing or from decreasing to increasing, that would be right there. Maximum value, maximum value, minimum value, and a zero. That's a pretty important one. So a zero is any time the function equals 0. Okay? So that makes sense. But when you look at a graph, where are the zeros? The zeros are here and there. Everywhere where the graph crosses the x-axis. Those are what we call zeros. So knowing the zeros of a function is really convenient for graphing that function and understanding some of the characteristics about it. So we've got one here that we can do. The sun rises at 6 a.m. So we're going to draw a little thing here. Reaches its highest point above the horizon at 12 and sets at 6 p.m., which looks like they are going into military time, so that's cute. And reaches its lowest point at 12 a.m. 1, 2, 3, 1, 2. Do you like my drawing skills? So this is a rough guesstimate of what they're talking about here. Now, it's not exact because we don't even have y values here, but some of the things that it points out, so the sun is rising at 6 a.m. So if our y was like the height of the sun in the sky or something like that, it would be increasing up to here. And then at 12 p.m., it reaches a maximum, which is right there, and then begins to decrease. And this negative part, how do you have negative distance? Well, in this case, that's the sun going even further below the horizon, which we know because we can call somebody on the other side of the world. And the graph is decreasing right there. So I was able to use some of the characteristics that they gave me to make that graph. And this is what we just talked about. And the only thing we forgot to do was our 0. So I missed a little bit on my graph, but our zeros would be, we would have one right here, and one on the next day right there, but we don't really talk about that in this situation. So again, anywhere where the graph crosses the x-axis, the x-axis, and in this case, it would be even with the horizon. So I always like to put things into context because it helps get us ready for actually being able to solve real problems, which is kind of what math is all about. More characteristics of functions, including average rate of change. And it says in context, which is kind of something we should always do, but I guess I had to say it out loud. So the average rate of change is, on average, how much does something change? So here's your formal definition. The average rate of change is the function over an interval, AB, is the ratio of the change in function of values, f of b minus f of a, to the corresponding change, the x values, b minus a. So the average rate of change, blah, 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 blah. Yeah, so feel free to read that 10 times over, and you probably still won't understand it. So that being said, I should point out, so getting familiar with this math language is definitely an important concept that I would encourage you to do. And so reading these definitions and really picking apart what each part of it means is a really good concept to do. Especially if you are going into the STEM fields, science, technology, math, engineering, things like that, you're going to see a lot of this type of language. If you have no desire to do any kind of math after you're done in college or high school or whatever, then, it is what it is. But anyway, average rate of change. So if you have a function, the way I remember it, and this is my science brain kicking in, delta also stands for change. Change of x over change of y. Or to use their words, is the corresponding change of the x values, b minus a. So the average rate of change is positive on a to b when, okay, blah, 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 blah. So it is the ratio of the change of the function of values, f of b minus f of a, to the corresponding change in x values. So they're saying instead of change of y, they're going to do change of x over change in f of x, which is probably a little bit better way of saying it, but whatever. So let's see what we got. So the table models this table. 1 day's predicted tide heights. So in the ocean, the tide comes in, tide comes out. Predicts tide heights in relation to the mean low water level or MLLW. That's weird. But at Weymouth 4, River Bridge, Massachusetts. So here's your baseline. So low tide is still a little bit above your baseline. High tide is way above your baseline. And so your tide goes back and forth from there. Thanks, Moon. So height is above the lower water level line. And then, you have your maximum here. Looks like we have, oh no, not a maximum, never mind. Maximum here. So plot the data on the graph and sketch a smooth curve through all the points. So all we're going to do is we're just going to take each one of these, 12 a.m., 1.9. So 12 a.m. is probably going to start here, and we'll say 1.9 is right there, kind of close to 2. Like that. And let's do it. So here's our first one at 12 a.m., 1.9 or whatever. And kind of goes down, and they kind of made that part up. But here's your next line, and then they just had a smooth curve going back and forth. And this helps us see some of our characteristics. Again, maximum, minimum, whichever one is lower is going to be your minimum. But the tidal range is the difference in height between consecutive high and low tide levels. Which observation can you make about the tidal range at this site? So if we look at our maximum, that's around 10. Our minimum is around like 2. Tidal range appears to be between 1 and 11 feet. I like that idea. Wow, maybe not. Oh, so it's a difference. So so if this is 10 and this is 1, so try again. We'll go with that one. So yeah, I just didn't subtract it out. Turns out I'm not always right. What is the average rate of change between the first low tide and the high tide following it, and the average rate of change from the second low tide and the high tide following it? So here is our low tide, and here is our high tide. So I'm just going to come up here. Let's see, what times were those at? So we could probably use 12 a.m. and we can probably use 8 a.m. So I'm just going to look up what those exact values were from the charts. 8 a.m. is 8.66. 12 a.m. is 1.19. And what is this? The average rate of change between the first low tide and the following high tide. So the average rate of change is going to be change of our y, over our change in time, so change in x. So I'm using context to say that it's going to be something more like that rather than what I said earlier. So that's going to give us, and if you look at our units, it'll make more sense. That's going to give us feet per hour, right? That seems like a good thing to have. And if you need further realization in context, it's given feet per hour, so that's what we're going to do. So we're going to go this one minus that one. Okay, so 8.66 minus 1.19 over 8 a.m. And we're going to convert all this to basically like our time. So our 12 a.m. is going to be 0, and then our 8 is going to be 8. So that's going to be minus 0. So 8.66, 8.66 minus 1.19, 7.47. I'm so good at basic arithmetic over 8. So then we can plug this part into our calculator and get a single number, which is probably what they want. Yeah. So this is a little trick on our calculator. We have the answer already. So you can either just push the divide by and it'll automatically put the answer, or there's always this answer button right here. So if you push second answer, that will just take the answer that's directly above it. We're going to do divided by 8. That's going to give us 0.93. Is about 0.93 per hour. That was the first one. Now I got to do the second one. So this one is at, we'll say 1300 or 1 p.m. right there. And then this one's going to be at 2000, which is like 8 o'clock p.m. So 8 p.m. is going to be 10.25, and then 1 p.m. Let's use the 2 p.m. one since we have that exact value. So we're going to change that to 1400. We're going to say 1.27, and we're going to do the same thing. So change of y, 10.25 minus 1.27 over, I'm just going to say 2000 minus, what is that now? 1400? 14. So then, if we wanted to skip all of the basic arithmetic steps, we can plug all of that into our calculator, like so. So parentheses are your friends. Remember, parentheses always happen first, and so we want this top part to happen first. 10.25 minus 1.27, close parentheses. We want to divide all of that by this thing, but we want the 20 minus 14 to happen first. So parentheses are your friend. You will hear that in pre-calc a lot, FYI. So 1.50, we'll say 1.50, 1.50. See what our options are. 1.50. Woo! So what is the average rate of change between 6 a.m. and 6 p.m.? Round to the nearest hundredth. So again, we're just going to come up here and say, so that's going to be 6 a.m. and then 6 p.m. is going to be 1800, or 18 in this case. So 6 p.m. is 9.13, 6 a.m. is 8.57, and so, just like we've been doing, 9.13 minus 8.57 divided by 18 minus 6. And again, I'm just going to shove that whole thing into my calculator, because parentheses are my friend. Minus 8.57. So I say parentheses are your friend because your calculator will always do the proper priority of work, whatever the word is, I can't remember right now. But 0.047. What is it? Raised to or rounded to the nearest hundredth, tenths, hundreds. So 0.05. Let's see if that works. Yay! So notice how the average rate of change, if we come back up here, between 6 a.m. and 6 p.m. is not that much. Even though it goes all the way down and then comes all the way back up, the average rate of change is going to be just that straight line. It doesn't matter what happens in the middle, it matters where it ends. So more characteristics in context. This time we are dealing with a car's suspension system. So suspension system is basically a glorified spring that connects the body of your car to its wheels. The springs are one component of the suspension system. The graph shows the vertical displacement of the spring in a car's suspension after the car hits a bump during a suspension test. Identify and interpret key features of the graph. So one thing I forgot to mention earlier is, so we have a maximum and a minimum, but we also have another maximum and another minimum. So we have another maximum right here and another minimum right here. So the difference here is this is an absolute maximum, and this one is going to be an absolute minimum, or a global maximum or global minimum. Both of those words mean the same thing in this context. And then these two right here are what's called a local maximum and a local minimum. So those are kind of important, more characteristics to note that can tell us about the function, even though it's not a global maximum or minimum. So let's see here. The greatest change in spring position occurred within the first 0.2 seconds, hitting a bump. The graph shows a maximum minimum value at 0 and okay. Cool. How can the displacement value at 0 be a maximum value when it is not located at a turning point? The value at 0 is a maximum value because it is greater than all the other displacement values. Yeah, so maximum and minimums don't necessarily have to be at a turning point, but local maximum and minimums are generally always at a turning point. The lowest displacement is about 0.035 meters, occurring at 0.2 seconds. The graph also shows a minimum value at 0.65 seconds. What makes the displacement at 0.65 seconds minimum value when its displacement is less? So that's again, so this is a local minimum here. This is a global minimum, and it's a minimum you can tell because it's a turning point. So there's a turning point at 0.65 seconds where the graph changes from decreasing to increasing. That's when we want. So from decreasing to increasing, this would be a minimum. How can 0.45 second be part of both an increasing interval and a decreasing interval? Because it's a turning point. I think that's why. And again, typically, I think a lot of times at turning points, like 4 or 5 right here, they would not include that in the actual interval. But in this place it is. So the average rate of change for its first maximum and first minimum is about, hey look, they did the math for us. That's neat. Does this rate of change accurately represent the entire graph? So that is from 0 to 0.2. 0 to 0.2. So what do you guys think? This rate of change, does that accurately show the rate of change for the entire graph? I hope the answer is no. The graph has increasing intervals, so a better representation of the entire graph should be a rate of change on an increasing interval. No, the graph has intervals of decreasing and increasing, so the average rate of change of only a decreasing interval is not representative of the graph as a whole. So what they're saying there is we took the average rate of change of just this fall right there, and then we didn't take into account that there's an increase here, another decrease, another increase, another decrease, and then it probably levels off because that's what a suspension is supposed to do. So that's all that's saying right there. All right, last one. Apply function characteristics to a real-world context. What do we got going here? A description of a real-world situation can be used. Okay, cool. Yeah, neat. So we've got a roller coaster, maximum elevation of 205 feet. The roller coaster ride begins at ground level. The first 40 seconds, the ride includes only turns with no changes in elevation. Next, the roller coaster rises steadily for 50 seconds to a maximum elevation of 205 feet, then plunges back down to ground level in only 8 seconds. In the next 6 seconds, it rises to an elevation of 100 feet, then drops back down to the level in the 6 seconds that follow. The remaining 9 seconds of the ride includes small inclines and drops before returning to its starting point. So you can use that information even though you don't have exact numbers. So the first 40 seconds, it only includes, so it stays at ground level. And then, so let's see here. Then the roller coaster rises steadily for 50 seconds to a maximum of 205 feet. So 205 feet would be like right there, a little bit lower. And then it rises steadily for 50 seconds. So that's going to come this line. Okay, and then it plunges back to the ground level in only 8 seconds. So this is 90 seconds, and this is 100 seconds. And it said what, 8 seconds? So it's coming all the way back down here, and we might need to like round a little bit. Almost straight down. And so if you see how I'm going through each one, I'm putting the information that we have onto the graph. So let's see what we got. So this is probably a little bit better, more accurate graph than what I'm going to draw. So there it is. But again, here's a steady rise, the fall, the immediately going back up, the fall, and the rest of it just all the way home. So let's match the unit and scale to the axis. So the x-axis is this one right here. What is that? Going to be time in seconds, which leaves elevation in feet to the y-axis. How does the description of the scenario allow you to identify important values on the graph? So the scenario gives us a lot of the maximums and minimums and things like that. So that's one of the ways that I was using to make the graph. I'm not going to type that out because I think your time is better spent elsewhere. So why is the part of graph from x equals 0 to x equals 40 horizontal? Because the roller coaster, it was moving. That didn't really tell us about the speed. The graph is horizontal because the roller coaster is at the same elevation. It's what we read in the description. What are the average rates of change of the two greatest drops? Round to the nearest tenth. So we're going to come back up here. We're probably going to use the data a little bit. Our first drop went from 205 to 0. So if we're going to do change in y over change in x, that translates to like y2 minus y1 over x2 minus x1. I'm writing it in a way that I'm hoping you've seen before, but if not, whatever. So y2 is where it ended is 0 minus 205, and then it plunges back to ground level in only 8 seconds. So what that tells me is that our change of x is 8. So of course you can look at this graph and do the calculation, but it tells us that this part right here is a total of 8 seconds. So that's why I can get away with doing that. So we're going to have a negative number. Does that make sense? In this case it does, because the rate of change is you're dropping, you're falling in elevation. So that's what that negative number means. So let's go ahead and throw that into the calculator. Negative 205 divided by 8 equals a number, negative 25.6. Hopefully that's rounded enough. Yay. Average rate of change of the second drop. So again, let's see if we have some actual data points we can do. In the next 6 seconds, it rises to an elevation of 100 feet. So we'll do this one in blue. So it starts at 100 feet. So that's going to be our y1. Then drops back down to ground level in 6 seconds. So again, same concept. It's giving us our change in time, 6 seconds. So we take negative 100, negative 100 divided by 6, and we are going to have negative 16.7. So now we can answer the question, like, which drop was faster? Which one were you moving faster in? And the answer to that would be the first one. Which is what they're asking right there.